All right, welcome back everybody to the third and final part of our series on kinematic equations of projectile motion using Fortnite grenade launcher as an example. We're going to get right back into it, starting with what happened last time, and then we're going to continue from there.
Okay, so last video we started by shooting a grenade launcher at 45-degree angle, and we stopped it right at the peak. And then using that, we calculated the time that it took to get to the peak and the vertical distance to the peak. And now you may be asking why the heck we did this. Well, it's to calculate the total distance that the grenade will travel as it continues its flight and then hits the ground. So that's what we're going to calculate next. But hold on, we've gone too far. Roll it back till about right there so we can easily see where the grenade impacted the ground. And that is where we're going to start. And as usual, we're going to start with finding out and determining what we know. Well, at the ground, what do we know? Time that it took to land, TL, well, we don't know that. But we're trying to solve for that. The distance, the horizontal distance it took to get there, well, we don't know that either. That's what we're trying to find out. And that's why we did all those peak calculations before. Now let's go to where we shot it from. What do we know? Well, the most important thing that we know is the velocity at which the grenade exited the launcher. The vertical velocity we calculated to be 11.1 meters per second, which is the vertical component of the total velocity of like 15.6, I believe, meters per second. And the horizontal velocity, because we shot it at a 45-degree angle, is the same, 11.1. Easy. Okay, now let's go back to the peak. What do we know and what did we find out from there? Why did we have the entire last video? Well, we calculated the time that it took to get to the peak, which is 1.13 seconds. And we also calculated the vertical distance, dyp. Be careful about your notations. And that, I believe, was 6.28 meters. Lastly, let's talk about the velocity at the peak. That we calculated to be the vertical velocity, mind you. It's always zero, right? Because it's the apex of the flight. It's switching from positive vertical velocity to negative, and right at the instant, it's zero. Okay, so now we have everything we need to calculate the time of landing. Now, basic physics tells us that whatever goes up must come down. And because gravity is the only force acting on it, it's actually going to take the exact same amount of time going up as it takes to come down. Don't take my word for it. We're going to use some kinematic equations to figure that out. What is the time at landing? So top left, we're looking at a new kinematic equation, which is the distance equals the initial velocity times time plus 1/2 acceleration times time squared. This is the fourth and final kinematic equation that we're going to be going over in this series. What do we know? We're going to use the beginning time as the time at the peak. And the end time is the time at the landing. This is why we stopped at the peak, because we know V0, the vertical velocity at the peak, we know that's zero. And so that makes it really easy for us to cancel that out. Lastly, we didn't state it before, but if we're starting at the peak and ending at the ground, the distance of the ground, dyl, is zero, because that's kind of our reference frame, that's our floor. So now let's use this, rearrange the equation, to use what we know. Distance in this equation is the total distance traveled from our starting point to our ending point. In this case, we're talking about from the peak to the ground. And that means that we need to convert distance, d in our equation, to the difference of the vertical distances between the two. So that's going to be actually final distance or height minus the initial height. So that'll turn out to be dyl, which is 0, minus dyp, which is the vertical distance of the peak. So we replace d with the distance traveled in our actual example. And v0 is replaced by vyp, the vertical velocity at the peak, which is 0. Great. Time. That's another key one. Again, it's going to be the difference in time between our starting point and ending point, which is time at landing minus time at peak. We simply had to finish the equation, replacing t with t at the ground minus t at the peak. And for simplicity, moving forward, instead of having these two TL minus TP, we're going to call it T2. Just call it T2 for now, and then we're going to use that substitution later. Basic algebraic substitution. All right, just like every other one we've done, we now rewrite the equation using these substituted values. So it's distance on the ground minus distance at the peak, or height, equals the vertical velocity at the peak times t2, our substituted value, plus 1/2 acceleration t2 squared. Now we get a sub in the values for these because we know all of them. First of all, again, I've said it before, but the vertical velocity at the peak is 0. So that cancels out that entire first part of the right-hand side of the equation. That turns to 0. So now we just end up with the distance, change in distance equals 1/2 at squared. Simple. Now, we're going to do a little rearranging so that we can calculate the time of landing, or t2 in this case, which is what we're going for. And so we're going to multiply both sides by 2, divide it by acceleration, and that will equal t2 squared. Take the square root of both sides, and that gives us t equals the square root of everything original on the left-hand side. So the distance on landing minus the distance at the peak, all of that times 2 divided by acceleration. And that's our equation for time. Fill in the numbers that we know, and that'll be time equals the square root of distance at the ground, which is 0, minus distance at the peak, which is 6.28 meters. We stated it before. All of that times 2 divided by gravity, which is 9.81 meters per second squared. Plug it into the calculator, and we get our answer, which is, surprise, surprise, 1.13 seconds. And so let's explain that again real quick. That's the exact time it took from shooting the grenade from the ground to its peak, and the exact same time it took from the peak to the ground. And that's just, you have a constant acceleration going up as you do going down, so there's no reason why time would be different going up as it is going down. Now, t2, which is what we calculated, is the time from the peak to the ground. But really what we care about is TL, time at landing, which is the total time it took from when we shot it to the ground. So we just substitute in that equation that we did for t2 before, so t2 equals t at landing minus t at the peak. Add in the values we rearranged to get t at landing equals t2 plus t at the peak, and it's basically 1.13 plus 1.13, and that equals 2.26 seconds from the time we shot it to the time of landing. Finally, we want to calculate the total distance that we shot the grenade. And we're going to go back to one of our old trustees of our kinematic equations to do that. So that'll be distance equals initial velocity plus ending velocity divided by 2 times time. We've used this before a couple times. It's one of the most basic and simple ones. It's just distance times velocity times time, or average velocity times time. And so substitute in our values in this equation. So that's distance dxl, which is the total distance, horizontal distance traveled, equals vx0, which is the initial horizontal velocity of the grenade, plus vxl, which is the ending horizontal velocity, divided by 2 times time. Or time TL, time it took to land, which we just calculated is 2.26 meters, or 2.26 seconds. Now, reminder when we substitute in these values, so dxl equals 11.1 meters per second, which is the starting velocity, and it's also the ending velocity because we're talking about horizontal velocity right now, because we are assuming that there's no force other than gravity, which is a completely vertical force. So that means velocity won't change at all. Divide all that by 2, multiply by time, which is 2.26 seconds, throw it all into a calculator, and you get 25.1 meters. And that's the total horizontal distance, or distance along the ground, that grenade flew from where we shot it to where it landed, which is essentially where you want your zombies to be, or your other player, or whomever. And so this is a great example, and this finishes our example of how to use kinematic equations of projectile motion to play some Fortnite. You're not going to use it in the game, but essentially you're doing that by instinct. Okay, so quick review of all 3 parts of the series. We're going to talk about the different equations that we learned here. First, it's v equals v0, initial velocity, plus acceleration times time. And you'll notice that all these equations, when put side by side, are very similar. It's because they're derived from the same principles of distance equals velocity times time, or velocity equals acceleration times time. They're all just derived a little differently and in different combinations so that you can solve all kinds of different problems. The second one is distance equals the average velocity times time. So v0 plus v divided by 2 times time. The third one, again, very similar, is v0 initial velocity times time plus 1/2 acceleration times time squared. And the last one, we're going a little out of order from where we learned them, is velocity squared, ending velocity squared, equals initial velocity squared, v0 squared, plus 2 times acceleration times distance. And these four equations make up the kinematic equations of projectile motion that we learned today, which is probably one of the first subjects you're going to learn in physics when you go, and one of the most interesting ones you're ever going to learn, because they're so applicable to everything we do. We use a grenade launcher here. It's the same thing that happens with a bullet shot out of a sniper round, a missile fired up into the sky, a ballistic missile, all kinds of stuff, throwing a baseball, throwing a football. Any of these things can be described by the kinematic equations of projectile motion. We just like blowing stuff up, so that's what we used here.
In the end, I hope you found that extremely educational, learning kinematic equations of projectile motion, which is a physics concept that we learned while playing some Fortnite. I find that pretty exciting myself, and that's exactly what we're trying to do on this channel. We're trying to bring education on one side and combine it with video games, which is something that people love doing anyways, to add some more concrete examples to what you're already learning in school. So thank you again so much for watching. If you liked it, of course, hit subscribe, hit a like, and add some comments down below about what you want to see next. Games, learning concepts, whatever it may be. So thank you again. Have a good day. Goodbye.